All right, so the last time we talked about the alkylation. So I gave you one example. You can try to do this way with some the catalyst. You can try to alkylate your aromatic compounds. This looks like. So we also talked about the full limitations about the alkylations, what we're gonna do next today is very similar to alkylation. So we're gonna call this acylation. So we're gonna put the acyl group on the aromatic compounds. So if you have anything looks like this, that is your acyl groups. So basically, only difference you're gonna do on this one is you have a specific group that will substituting your hydrogen over there. That's pretty much it. So you have this one, and then you have a little bit of a high temperature. So it's pretty much the same. What happened to this one? Let me give you one specific example. Putting this one R group to the methyl group here. So if you do this one over here, what happened to this one is whenever you have this part actually goes to in this way. So if you look at this one over here, this will become AOCF4 negative. Okay? You see this one goes over here, and this one goes to this compound here, become luminous tetrachloride and negatively charged. So if that is happen, so when they break apart, this part all together, do you going to have this one? See, this is all gone to here, and that goes to there. So these two are now we have. Okay. So as we know, if you have some good electrophile, you can use it for this aromatic electrophilic aromatic substitution, which could be here. So they can either go this way because there's a lone pair on this oxygen here. They can go this way, back and forth. But anyway, that makes very good electrophile with the positive charge. So that happens. This one, you see the pi electron, this double bond will tag this one, which is electrophile, which is good. So it can tag here. So what we get to, so double bond is gone, right? And you got to this one here, okay? And then you have this one comes in to grab this one as a base, kind of behave like a base. And then there's the pair of electron were bound to carbon and hydrogen here, or can be in the original, the pi bond there. So it can make a double bond again. So this will picked up by one of the chlorine anion in this compound. So will become double bond again here. Oh, so yeah, sorry. Once again, you see there will be positive carbocation here. But once that goes to there, that makes the double bond now. This is gone. It makes HCl plus. It's very similar to what we've done for the alkylation again, this is acylation. Acyl group will be substituting one of the hydrogen in your aromatic compounds. All right, so that's pretty much it. This is very similar to alkylation. Maybe if you have some time before the exam 2. Do you know when is exam 2? It's early April. I think it's the 7th or 9th of April. So we still have quite a time, we'll definitely do this again on the review session. But basically what we did was try to find a really good electrophile that can be attacked to by the double bond in the aromatic compounds So they can be substituting the hydrogen by simply remaining hydrogen and pick up by that other base. Okay? That's pretty much. Okay? Does it make sense? Okay. All right. So the next part, we're gonna learn about the substitution group effects. So whenever you do this, for example, we learn about the nitration, sulfonations, and alkylation, isolation, halogenation, so forth on this aromatic compound. And if we have a certain groups on this aromatic compound, maybe you can say it's a Y group. If there's any substituting group on the aromatic compound, we may just change the speed or the reactivity of the reactions. Let's take a look over here. So if you have, maybe this is the Y group here. So if we had Y group was NO2, okay, and then we have groups that was the Cl, well, halogen or hydrogen, and then you have over here. Okay. So in that case, you're going to have a different reactivity based on the what substituting group are attached to your aromatic compound. So this is about very low number. So here, this is our standard. This is number 1, meaning if that is the speed of, if that determines the speed of the reactions, this will be our standard as 1. So if that is 10, means that reaction is 10 times faster. Okay. So, but this is our standard, so we're gonna put this one as 1. Okay. And then, if this is 1, it will be this small number. Okay. So it's very slow. And this is the semi-slow, maybe like 30 times slower because it's 0.033. But if you have a hydrox group over here, that is going to be 1,000 times faster than this one. So that, if that was the nitration. So if you're gonna put the nitro groups on the aromatic compounds, if you already have this group over here, then it will be really, really slow because of this nitro group on your compound will have some effect on your compounds. But if you have just regular benzene, it's okay. But if you have a hydroxy group over here, nitration reaction on here will be really, really fast, like 1,000 times faster than the one is just benzene compound. Kind of makes sense. So if it is nitro group here, this reaction will be really, really slow. So if you're gonna add one more nitro group here, it will be really, really slow, like this much slow compared to what you have for the benzene. Okay, and if you have a halogen group here, you can probably do nitration too, but it's quite slow too. It's almost 30 times slower than the benzene compound. And then if it's a hydroxy group over there, which will actually make very fast nitration reaction. So those type of effects that we have for the aromatic compound, we call substituting group effects. Kind of makes sense. So whatever the group you already have on the compound will determine the speed of the reactions. If it's nitration, sulfonation, everything, this is the job we need. Okay? So I'll show you the something, but obviously you don't have to memorize. Okay? I'll show you this in the table on your exam. Okay? But you can just try to copy me. don't have a space. Okay, I'll move on to. Okay. That's interesting. Okay, so sorry, I don't have a space, but this is the, if you have okay, so if this is the left side, is a very low in activity. So the one on the right side is very reactive, if it's on the compound. So this is from here to here to here, okay? So this is the most reactive here. This is the most least reactive. Okay? So you don't have to memorize this one, but I'll put this on the exam. But I just want to show you what the groups are. Okay? So if you look at this one over here, this is what we call meta-directing deactivator. This part here. And if you see there's a halogen group over here, this is what we call ortho para directing activator, deactivator. Sorry, deactivator. I'll tell you why I was a bit confused, but yeah, deactivator. So this meta-directing deactivator, ortho para-directing deactivator. And this one, the most reactive ones, quite reactive ones, is ortho para-directing activator. So it means, what I mean by meta-directing or ortho para-directing is the, if you have, for example, hydrox group over here, okay? You have a hydrox group over here. You're going to have a substituent group added on either ortho or para, either way. So that's why we name it ortho para-directing activator for this one, ortho para-directing deactivator for halogens, and the meta-directing deactivator for those two. Okay, so if it's a hydroxy group, it's right here, right? So it means it's ortho para-directing. So whenever you substituting the hydrogen on the compounds, it is going to be replace the hydrogen on the ortho and para position. Make sense, right?
No.
So no? Okay. Okay, yeah. So the substitution group effect is if you have a certain groups on the aromatic compounds, they will direct where your substitution would happen from there. Okay, so those are the one we call meta-directing deactivator. This is the one we name ortho para-directing deactivator, and this is the one we name ortho para-directing activator. So if you look at this one here, okay, you have a hydrox group on this aromatic compound here, right? Right? So whenever you do the substitution here, this one will become on here or here, either way. Because this is an ortho para-directing activator. Makes sense, right? Okay. So, but if there was the benzaldehyde, which is here, okay? Benzaldehyde. This is a meta-directing deactivator. So if you do this, it will be on meta position. This is And also, once again, this scale means reactivity. So if this is not so reactive, some are reactive, quite reactive over here. Okay? Yeah.
On the chart that you're going to give us on the test,
Yeah. Oh.
tell us which one is ortho compared to one.
Absolutely. So once again, don't worry about the chart. I'm just doing this for you to explain. But this will be given, obviously. You don't have to memorize. Don't worry about it. But only thing that I can't, so I'll tell you some tips that how you can do this easily. If you look at those here, those are the one we actually call electron withdrawing groups. Okay? So I'll tell you why is electron withdrawing groups over here. And these halogens are the activators are electron donating groups. Okay? So if it's that was actually a really good question. So I'll give you this. Don't worry about it. But whenever you look at it, this is how they kind of arranged it. If it's electron withdrawing groups, it's less reactive, so on the left side. If it's the electron donating group, it's more on the right side of the scale, which is more reactive. Because think about it. If you think about the aromatic compound, it's simply silane compound with all pi electrons are conjugated in the ring structure. So if you have any groups that is withdrawing the electron density in the conjugate density of the ring structure, your compound become less stable. Because they try to see the electron density, this substituent group on the electron ring groups on substituent group on the aromatic compound will try to attract those electrons in the conjugated pi electrons in the compounds. So then those compounds will become really unstable. So they don't want to go into carbocation position, which is one of the mid steps on your substitution. So that's why they're not quite directed. That's why they're located in the left side on the chart. But if you have a really good, the electron donating groups, like halogen groups, or all the groups that can donate the electron to the aromatic compounds, that makes more rich in the electron density in the aromatic compound. So that makes the aromatic compound in the reaction very stable. So this is why if you have these groups on your aromatic compound, that makes that compound more reactive for the substitution. So that was a very good question. And also, I don't want to confuse you, but this is only one factor. So I'm going to talk about the other factors. And I will tell you why those halogens are in the middle then. This is slightly deactivating still, even though it's electron donating groups. Okay? So we're going to talk about it, why is it that way? Okay? Why those are both electron donating groups, but why they're located somewhere in the middle, but on the right. Okay? So I'll try my best, but this will be quite a lot of things to think about. It's a little bit of a lot of things to compromise together. Okay, so when you listen to me now, very carefully. So this will be quite tricky, actually, to be honest. So this is one way you need to think about, but there's a lot of things we need to think about. Then you will understand, oh, why those groups are in this way. Then honestly, you don't even have to memorize, you just know by looking at the groups. But I'll give you a chart anyway. Okay, but this will be a bit tricky because there's other things we need to think about. Okay, but for this chart, give it. Okay? Kind of makes sense, right? Okay, so just yeah. Don't worry about it. We even got to the why is it happening that way. So I'll explain now. But once again, it's a bit tricky. So please listen to me very carefully. This is a bit tricky because this other than just electron density thing, you need to think about these two. So the first one is inductive effects. And the other thing is resonance effect. Okay, so I think the easiest one you can try is the inductive effects first. So let's try to do this one first. Okay, so we'll do the resonance later. So inductive effect, you know what the induction means? So induction simply means, for example, if you have this type of group over here, okay, and then here, okay. So if you have this type of compound here, this one will become better or stronger. It's a stronger acid than this, okay, and because of the induction, okay. So I'll tell you what induction really means. So induction simply means because of the electronegativity difference between each different elements in the compounds. If you look at the fluorine over here, which is located in the right top corner of the periodic table, means it's very highly electronegative. So when it's become really highly electronegative, means they have a strong power to pull the electron toward themselves. So it's not just about the neighboring carbon, but this whole compound. There's a lot of effects on not just the neighboring carbon, but in all the elements in the carbon in general. They have a slightly tend to those electron cloud on those compounds will kind of tend to more on this way because of this strong electronegative elements on this side on compound. Okay, so if that is the case, and this oxygen is also quite electronegative too, so that makes those electrons can be easily going into this direction because of this. Not a lot. So induction is not major force in here, because the major force will be actually oxygen here. But indirect, even the fluorine in the long distance can somewhat help this compound detach this hydrogen away easily. This is kind of minor effects. So this induction is not one of the really strong major effect, but one of the minor effect. Okay. Most important thing is the element right next to it. Kind of makes sense, kind of. So then means because of this one, it can be easily released. Proton can be easily released because of the fluorine over here. Okay. Then that makes stronger acid, because the stronger acid means if you can donate more proton, that makes that compound a stronger acid, right? You guys remember this, right? But here, they don't have a fluorine here. So only thing they will do is just this oxygen detach this one because it's more electronegative, but there's no additional help like it did over here. So this is slightly less acidic than this one. So this is induction. That is induction. Makes sense, right? Okay. So if you think about that way, all right. So let's think about this one. So I'll give you just a few examples here. If you have a chlorine, hydroxy groups, or nitro groups, okay? Okay, here. And then, well, think about it. This is looks like this. Okay. So if this is the case, the chlorine, like let's make it even stronger. Okay. So fluorine or oxygen, or there's the oxygen on this the group here. So because of those, but this is positive, so we'll actually ignore this one. Normally it's also very electronegative, but because these two electron, the oxygen and halogen groups over here, so I just put X there. This is the halogen groups. This could be anything, not just fluorine, but anyway, the halogen here. Because of the electronegativity, not just this carbon here, but whole conjugated electron density were kind of heading this way. Okay. So they're kind of going this way actually. Okay. So if that is what we call inductive effect. Okay. We haven't gone to the resonance effect yet, but this is why we have an inductive effect. But because of this halogen is quite electronegative, that is the reason why, even though they're going to behave like electron donating groups, because it's quite strong electronegativity, it only becomes slightly less deactivated. So it works, but not so fast. But this is somewhat explains the inductive effect. So one good example from this one is the toluene. Okay? So if you have this one, this carbon surrounded by 3 hydrogen here. So hydrogens are less electronegative than carbon. So means this carbon surrounded by less electronegative 3 hydrogen, but here this carbon is surrounded by this carbon, this carbon, this carbon. So very slight gap, but still this is slightly positive here and slightly negative here. So this is slightly negative, slightly negative, slightly negative, slightly negative. So going all this type of moment direction here. But this is quite one of the few examples it goes in this way. So inductive effect wise, those are deactivating. This is activating. But this is somewhere in the middle. This is still very strong reactive, even though it's inductively deactivating. This is also not good because it's electronegating here. And this is also actually widowing groups over here. So this will become quite strong reactive substituting groups. This is not so well because this is including inductive effect. This is also electron withdrawing groups. So this might be one of the worst case. This is kind of a bad inductive effect because the oxygen tried to get it, but this is electron donating groups, so that gets overcome. That this advantage become one of the good reactive groups here. I know it's confusing, but basically if you just look at the chart, it tells everything. But this is the one factor you need to think about, and that is the reason why this will become just in the middle, not on the right side. Does it make sense? So I'll move on, but I'll promise you I'll do this again some days. Okay. This is inductive effect. So let's talk about the resonance effect. Then. Resonance effect. Resonance. Let's look at the resonance structure. So resonance structure. First example I want to give you is following over here. Okay. So if you have this one over here, whenever you, for example, we have a nitration process. So when I had so we're gonna put this in the ortho position first. Okay, let's try to put the ortho position and meta position and the para position and see what happens to it in the resonance structure. Okay, and we'll actually tell you why is better on the ortho and para position when it's the methyl groups totally on here. So if you have a nitration over here, you're going to have this position here. Also, it's this position here, right? And then you're going to have this one. Okay. So that means you're going to have carbocation over here, right? This is what we've been doing, right? But we can also think about the possible resonance structure from here. Just try to remove relocated this double bond to here. Then you goes to here, right? And you're moving carbocation to this position here. Okay? Do you see this? So carbocation is here, but you can just move this double bond here, right? Then you're actually moving the carbocation position to here, right? Okay? And then you can also move this one to here. Okay? So then goes to here, here. Then it moves to here. Okay? So can you guys just see there's something happening here? So these two has the carbocation position in here and here, which they are surrounded by 2 carbons here, right? 2 carbons and 2 carbons here. Okay? But here, because of this methyl group, it has 1, 2, 3. So this is a more stable resonance out of those 3. Because of the 3 carbon. There's 2, but there are 3. So because of their more hyperconjunction and all the other induction, that makes this carbocation position more stable than the other. You guys remember this, right? Carbocation stability is more, oh yeah. So that is why this is more stable here. So maybe, yeah, we have this case over here. Okay, I don't have much of space. Okay, so can you guys copy this one? Copy this one. Okay, let's do meta. Let's do meta. So in this case, I'm gonna place this one, this go in the meta position here. I place it in the meta position. Okay. And then in this case, you're gonna have a hydrogen over here, and you can try to put the charge. Okay, looks like this. And then if you move this one to here, okay, if you move this one to here, it goes to in this position. Okay, this is another possible resonance structure. So you can go like a force here, right? And if you move this one again by moving this one in this way, okay? So then you're going to have here, okay? So do you see the difference between the first one and this one? So in this one, you have a carbocation here, here, and here, where you can only find the two R groups are surrounding this carbocation position. So unlike the first one, you don't have a carbocation that were neighboring 3 carbons, but only 2, 2, 2. Okay, so this one had a 2, 2, 3. This one is 2, 2, 2. So they don't have any prior stable, like a resonance form among those 3. They're all same stability. Okay, makes sense, right? Okay, so yeah, copy this one real quick. Okay. And the para position. So let's try to put it on the para position. So para position is here, right? Okay. So if that is the case, you're actually going to, it doesn't matter, you can put it in the here, okay, here, okay. And then you can move this one to here, okay. And then it goes to here, 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 okay. So you got this one over here. And then you can move this one to here. So you can move that one to the other carbocation position. Oh, sorry. Here, here. Okay. So now you have this one, and this one. And like we already saw in the ortho resonance, you also have a one that is most stable one out of those 3 resonance. Okay? Because of the 3 carbon, 1, 2, 3, there are 2 and 2. So this is a bit more stable than these 2. Okay? Okay? So think about it. Whenever you have a substitution on ortho and para, you had at least one carbocation is more stable, right? But in a meta position, you only have the carbocation position that only surrounded by 2 carbons, which is only somewhat stable. Okay, so that is why whenever you do the substitution with the toluene, with the methyl group on the substituent group, they will prefer to have those 2 products, but not so much on the meta position because of the resonance stability. Those 2 are a bit more higher stability than meta position 1 product because of this carbocation stability you can find in this possible resonance structure of those 2 scenarios. It kind of makes sense, right? Okay, good. So now you see why you have a methyl group or directing ortho or para position substitution, not meta. That is why. So if I give you one example looks like this, so I'll give you this one. Okay, and if I try to do sulfonation with this, you guys hopefully you guys remember this one. This is what we did on last time, and then you can predict to have two products. Looks like this. Okay. Which is your ortho position substitution and para. Okay, but not so much. Very, very little or almost none meta position products there, but just these two. Because of this method group, which is your ortho para directing activator. Okay. Okay. All right, so I'll give you three more examples, but it makes sense though, right? Makes sense, right? Okay. Okay. So let's talk about the halogens. Okay. So we have like chlorine or fluorine or those type of things. So if you try to do also nitration, let's try to look at why it's also and para activating. So there's one thing I want you to remember is that this is also it has a 3 lone pair. Do you guys know why now though, right? It's a halogen 7 valence electron. There's single bond there. There'll be 3 lone pair here. So those lone pair can be easily donate over there. Okay. So this is what we call this electron donating group. You guys remember this, right? Halogens and other hydroxyl, amine, or other methyl, or other ether groups are electron donating groups because this one, there's the lone pair, because the lone pair on the nitrogen or halogen or carbon there, oxygen. So anyway, so if this is the case, this is something I want you to remember. So let's do ortho. Okay, let's do ortho. We have two. Okay. So anyway, so if you do this one over here, I'll do real quick. I'll do this again on Monday. Don't worry. Yeah. Yeah. We're kind of running out of time, but let's do this again. Okay. So let's start to put ortho position here. So we put this one. Okay. So pretty much the same. What we're gonna do? We have a position over here, right? So this is good. And we're gonna move this one to in this way. It's pretty much the same. We're gonna do the same thing a lot. Okay. So whenever you do this one in this position, okay, and then you're now carbocation is this position here, right? And then you can move this one to this position, the double bond, and you can also have another resonance structure, looks like this. Okay, so in this case, what happened to this one is like I said, this is electron donating group, right? Halogen is electron donating groups. This one of the lone pair goes to make a double bond here. So this will be gone. Okay, so it becomes over there. So the positive charge on the chlorine now. So then that makes this part of your ring structure what? More stable. Because you don't have a cation in the ring anymore, right? It's now onto the halogen. So that's why this will become stable, more stable resonance. Okay? So obviously this will prefer the ortho position. It's the same actually. So if you do para and ortho, you'll get this one. So we prefer. If you do meta, carbocation cannot be located here, here and here and here. That's why you can have this form, which is not so good. So also in this halogen, directing ortho and para position, not meta. I'll show you how in detail anyway on Monday. But you kind of see why now. There's a lot of things we need to think about. So I'll do it again on Monday. Let's stop here. Okay, sorry.